So hello, in the 8th section of the strength of material interview preparations, let's talk about the deflection of the beam. So for this given situation where the beam is simply supported and there is a force in the center which creates the deflection, which is the beam, and it creates a deflection y, and this theta is basically called as slope, which is dy by dx. So from the moment of equation we can basically calculate the radius of curvature r. So for a particular case, the radius of curvature is constant throughout the beam, and that kind of situation is for the pure bending case, as we are seeing the earlier situation. So which is in that case, the moment is basically same throughout the beam, and there is a material constant. If it's a material constant, so in that case, the radius of curvature is constant throughout the beam. Okay. So there are different methods to find the slope and the deflection of the beam. So the first method is the double integration method. It's called Macauley method. Second is the moment area method. Third is the conjugate beam method. So in the Macauley method, basically this is the formula of Macaulay. So moment along the axis is equal to negative of the E times I, which is the fluxual rigidity, times the expression. So if we integrate this expression, so basically this expression is equal to negative of the moment of negative moment by E times I, which is the fluxual rigidity. So if we integrate it, we get this expression dy by dx, which is the slope theta. Okay, and if we double integrate it, we get the y, which is called deflection. So from this formula we can identify the slope and the deflection. Okay, so for given case like this, for the same situation here, so from this we can get the boundary conditions. So at this and this point, x is equal to 0 and L, so we can see that the deflection is 0 at the end, and the slope is not 0, and at the center point the slope is 0 but the deflection is maximum. Okay, so for that's an interesting case for the fixed beam condition. In this, the beam is rigidly hold here, so when we apply the force here, there is a high deflection here, but at these extreme points A and B, which is x equal to 0 and L, the deflection as well as the slope is 0. So this is the maximum boundary condition. So it's very useful for our calculations later. So from the Macaulay equation, at given section, we can basically find the bending moment at the given section using this formula. So from this formula we can basically calculate the shear force, which is nothing but the derivative of the bending moment, which is this expression, and we can actually find the force intensity, which is the derivative of the force. This is the expression. So next we go talk about the moment area method. So in this moment area method, we can basically identify the slope and deflection by this loading diagram. So from this loading diagram, we simplify this loading diagram by dividing it like this. So this is the fixed beam, but we simplify this as a simply supported. So we get the reaction force and the load here, and we take out the moment outside. So if we create the bending moment diagram, so this is how it will look. Okay, triangle shape, and for this case it is just a rectangle. So when we superimpose these two diagrams, so we just have to flip it out. So this is a positive area, when we flip it out, it becomes a negative area, and this becomes like this. So when we eliminate the area, so it will become the final medium becomes like this. So at these 2 points where the moment are changing from negative to positive and positive to negative, so these 2 points are called point of rupture, where the bend is happening. Okay, so bend is happening like this, and for this the diagram, the shear force diagram will be, for the moment area it's just line, for this one is just like this. So this, finally this will be shear force diagram. For this next case where we have the uniform applying load, so for this case and it is rigidly hold fixed beam, we simplify this as like this, simply supported and the moment. So for this case we have this medium parabolic, and for this we have just a beam. So when we superimpose it, we get such a diagram here. There are 2 point of ruptures. Okay, and for this kind of case, whether there's a twice load, we again simplify it. So we get the BDM for this something like this, and for the moment it is something like this. When we superimpose, we get the final BMD similar to like this. Okay. So the third method is the conjugate beam method. So conjugate beam method is nothing but it's an imaginary beam whose loading diagram is nothing but this diagram of the actual beam. So what happens is that we take the moment of the actual BMD of the actual beam. So we divide it by EI, which is flexibility, and we treat this diagram as the loading diagram. And from this loading diagram, we basically find out the shear force diagram as well as the BMD of the conjugate beam. Okay. So what we do is that from this we can basically calculate the slope and the deflection. So for the slope at any given section, we basically take the load, the shear force at a point of the conjugate beam, and for the deflection we take the bending moment of at the particular section of the conjugate beam. Okay, so this both slope and deflection are calculated for the beam, but this information to calculate this, we basically take information of the load and the bending moment from the conjugate beam. So for example, if we have a case like this, simply supported, so for this the bending moment diagram is something like this. So at the center of the maximum, the moment is reaction force times the length, which is WL by 4. Okay, but we treat this as loading diagram. So this right now this is a loading diagram, and we divide it by EI, flexure rigidity. So when we divide it by flexure rigidity, it becomes the center point, the moment becomes like this, but we are treating this whole thing as a loading diagram. So loading diagram is the load is equal to load at this point is here like this, and if you want to calculate the total load here, so the total load will be W is equal to L by 2 times this. So this is the total load over the beam. Okay, so if you want to calculate if this is a total load, so from this we can calculate the reaction forces RA and RB, that is the half of the total load, which is this expression. Okay, so the centroid of this half will be here, G is equal to, and this is the L by 6. This is centroid, and this is basically a conjugate beam loading diagram, shear force diagram basically. So next is how do we calculate the slope. So slope at point C, as we have seen earlier, where is the deflection is maximum, at that point the slope is basically 0, because at when slope is at 0 means at that point the shear force is 0. Okay, and then how we calculate the deflection at A and C. Deflection at deflection, that means Y at A and B, the deflection will be 0, that means the moment is 0 at the diagram. So as you see, the moment at this 2 point is 0, that means the deflection will be 0, but at the center, this is center, at this point we have the maximum deflection, the deflection I think but the moment bending moment at the conjugate beam. So bending moment at this point we can easily calculate. So we have the reaction force RA times the length with respect to this C point, it's anti-clockwise, it means positive, RA times L by 2 minus this load is there, which is clockwise, so it's minus the total load at along this centroid point. So we have to take half of this load times the total load times the distance L by 6. So we get the bending moment at this point. Okay, thank you.